So now I'm going to talk about my theory in relation to DNA acting as a quantum computer. When the atoms of carbon, oxygen, nitrogen and hydrogen come together to form a base in the DNA molecule, the valence electrons will be forced in some cases, but not all, to alter their spin state due to the Pauli exclusion principle. No two electrons can have the same atomic number, so when the valence electrons pair up in the orbitals of the combined atoms, the pair of electrons has to have complementary magnetic spin. That's to say that one electron in the orbital must be spin up and the other spin down. For instance, let's look at the valence electrons in nitrogen and oxygen before these two atoms combine into a DNA base. You will see that in the valence orbitals, which are not fully occupied, the electron spin in both atoms is spin up. When these two atoms come together, some of these valence electrons will have to flip their spin orientation in order to occupy an orbital now as a pair of electrons. Those three valence electrons in the 2p orbitals of nitrogen and the two valence electrons in the 2p orbitals of oxygen will have to decide which ones are to flip their spin in order that they may cohabit the same orbital in the molecule of DNA. It's a widely accepted principle in quantum mechanics that these valence electrons will remember whether they have flipped or not. Now, Pauli's exclusion principle only operates when the energy levels of the atoms are in the ground state. In other words, when the DNA molecule is at its lowest energy level, the atoms of nitrogen, oxygen, carbon and hydrogen will be at the closest together. The orbitals of the valence electrons will be at their minimum size, and all the valence electrons will be uniformly paired in one spin up and one spin down configurations. In 1970, Fritz Albert Popp, a German theoretical biophysicist, found that DNA absorbs and emits light. In fact, what he found was that DNA stores light. This stored light is released as very weak, extremely coherent biophotons. It is said that photons switch on the body's processes like a conductor launching each individual instrument into the collective sound. At different frequencies they perform different functions. When an atom absorbs light, the electrons jump to a higher energy level, and when it emits light, the electrons jump back down to their ground state. So when the DNA absorbs light, the electrons actually jump to a higher orbital. Essentially, the distance between the atoms increases to accommodate this. The DNA molecule expands, and most importantly, the electrons are no longer bound by the Pauli exclusion principle. Each pair of electrons in each orbital no longer have to be uniformly paired with one spin up and the other spin down. As soon as the DNA molecule absorbs energy from light, it is no longer possible to tell from the spin state of one electron what the spin state of the electron with which it was paired will be. Indeed, it's no longer possible to predict whether those two identical electrons are still paired with each other at all. Once the DNA molecule is in an excited state, it is not possible to say with any certainty that any electron is in the state spin up or spin down. Any one electron is actually in a superposition of an infinite number of states, and certain probabilities attached to these superposition states as to what state the electron would be in if we had the expertise to measure it. In the case of the individual spins of one electron in one atom, in one base of the DNA double helix, the probabilities of whether it would be spin up or spin down would be infinitely complex. These probabilities would depend, amongst other things, on whether it was spin up or spin down in its previous ground state, whether it flipped or did not flip in that previous ground state, and these same considerations for every previous ground state. And then all these probabilities would be correlated in an immensely complex way with every other electron spin in the entire DNA molecule. But the really interesting thing is, no matter how astronomically complex these probabilities would become, the processing could all come down to a Boolean algebra no complex than in a conventional computer. For instance, if a single spin was spin down in its last ground state and it was spin down in the ground state before that, then it would have a high probability of being spin down if its spin state were to be measured in its current excited state. This is where quantum computing comes in. Recall Pop's finding that light is emitted from the DNA as very weak, extremely coherent biophotons, and that it is surmised that these photons switch on the body processes like an orchestra conductor, with his baton directing all the individual instruments in his orchestra. This must therefore involve the DNA acting as a quantum computer to process the probability states of the electrons when the DNA molecule is in an excited state. The light that the DNA emits when the molecule falls back to the ground state, these extremely coherent biophotons, are the output of the quantum computing process. If this light is directing the body and brain's processes like instruments in an orchestra, then it is highly unlikely that these biophotons are the result of a random process of electrons dropping back to the ground state. Quantum processing is taking place and specific instructions are being generated.